The companies dominating artificial intelligence are not winning because of better models. They are winning because of infrastructure. The real advantage in AI is not the algorithm. It is the building the algorithm runs in. Massive compute clusters, power distribution systems, fiber networks, cooling architecture. These systems cost billions to build, and once they exist, the economics of competition change. Because in many AI markets, the company with the largest infrastructure becomes the lowest cost producer, and the lowest cost producer rarely loses. In most industries, companies compete with products. In AI markets, competition increasingly revolves around infrastructure, not software features, not algorithms, infrastructure, compute clusters, data pipelines, energy supply, network capacity, storage systems. The capital required to operate these systems has quietly become one of the strongest competitive barriers in modern markets. Infrastructure moats do not rely on brand or intellectual property. They rely on scale. Once infrastructure exists, the economics begin to tilt. Larger systems often become cheaper systems. When cost advantages compound at scale, competition becomes structurally asymmetric. To understand AI competition, we have to look beneath the software layer, the rise of infrastructure as economic moat. Traditional software businesses approach near zero marginal cost. Once the product exists, additional users add almost no expense. AI systems behave differently. Running modern models requires heavy computational infrastructure. Every query consumes compute cycles, memory, energy, and network capacity. These costs accumulate. As AI usage grows, the infrastructure supporting it expands dramatically. Infrastructure therefore becomes part of the cost structure. Companies operating larger systems often achieve lower unit costs. Infrastructure economies of scale begin to appear. Scale produces several economic advantages. The first is cost efficiency. Large data centers distribute fixed costs across enormous volumes of inference. Cooling systems, energy procurement, and hardware utilization improve as systems run closer to capacity. Higher utilization lowers the cost per computation, but scale also produces a less visible advantage: speed. Infrastructure moats are not only about volume, they are about latency. In large AI systems, response time partly depends on physical distance. Signals travel through fiber networks, switching nodes, and regional backbones. Each step adds milliseconds. At small scale, the delay is minor. At global scale, it becomes economic. Large infrastructure providers place data centers close to population hubs and connect them directly to fiber backbones and regional power grids. The result is low-latency inference, faster responses, smoother interaction, near real-time systems. A smaller competitor renting distant cloud capacity often cannot replicate this experience. Because latency is not only a software problem, it is physical. Distance between infrastructure and user becomes part of the moat. Edge networks, fiber routing, and geographic distribution become strategic assets. Infrastructure determines not only cost, it determines speed. Scale also produces capital durability. Once infrastructure is built, replication becomes slow, not because it is technically impossible, but because it is financially heavy. Infrastructure is capital, and capital takes time. Building competitive AI infrastructure requires GPU clusters, high-density networking, power systems, cooling architecture, and large facilities. These investments often reach billions. But the barrier is not only the upfront cost, it is the upgrade cycle. AI infrastructure depreciates quickly, model architectures evolve, hardware becomes obsolete. Maintaining competitive infrastructure requires continuous reinvestment. The moat is sustained by capital flow. Infrastructure also introduces a strategic constraint. It takes time to build. A modern data center may require 2 to 4 years to construct. AI models evolve far faster, often improving every 6 months. This creates a deployment trap. Firms must build infrastructure for model architectures that do not yet exist. Hardware is purchased years before workloads are fully known. Power capacity must be secured before demand appears. Infrastructure is built for the future, and that future is uncertain. This creates a build-to-utilization lag. For a period of time, infrastructure may remain partially unused or mismatched with new models. For smaller firms, this is dangerous because depreciation continues regardless of utilization. Large firms can absorb the uncertainty. They can afford to be wrong for a year, sometimes longer, while models catch up to the hardware already deployed. Time itself becomes a capital expense, and the ability to absorb that delay becomes part of the moat. This reshapes market structure. When infrastructure determines cost advantage, competition becomes capital intensive. Large technology firms gain structural advantages because they can deploy capital faster and at greater scale. Smaller competitors face different choices: rent infrastructure from larger providers, or operate in niches where scale infrastructure matters less. This explains why many AI startups rely on cloud infrastructure rather than building their own. The capital required to compete at infrastructure scale exceeds the resources of most firms. Infrastructure ownership therefore becomes a strategic position, not merely an operational decision. Once infrastructure scale is achieved, the moat deepens. Lower costs allow companies to serve more users, train larger models, run more experiments, and improve performance faster. Each advantage reinforces the next. More usage increases utilization. Better utilization lowers cost. Lower cost attracts more demand. Demand increases usage again. Infrastructure scale becomes self-reinforcing, not through marketing, through economics. In many AI markets, the company with the largest infrastructure becomes the lowest cost producer, and the lowest cost producer rarely loses. Infrastructure also creates another advantage: talent. The best AI researchers gravitate toward the largest computational environments, not only for salary, but for access to scale. Training large models requires enormous experimentation budgets. Engineers want environments where their ideas can actually run. A firm operating a massive compute cluster offers something unique: a laboratory of scale. This creates a feedback loop between infrastructure and human capital. Top infrastructure attracts top researchers. Top researchers build stronger models. Stronger models justify even larger infrastructure. Over time, talent concentrates around the largest compute environments. The infrastructure moat becomes an intelligence moat. Companies do not just buy chips. They attract the people capable of pushing those chips to their limits. Infrastructure moats are not permanent. Two forces can weaken them. The first is commoditization. If infrastructure becomes widely accessible through cloud platforms, ownership advantages shrink. The second is technological change. New architectures may reduce compute requirements. If models become far more efficient, the scale advantage of massive infrastructure may decline. Infrastructure moats therefore depend on sustained computational demand. When compute intensity remains high, infrastructure dominates. When compute requirements fall, the moat can erode. Infrastructure as economic moat reflects a deeper shift in AI markets. Competitive advantage is no longer determined solely by software innovation. It increasingly depends on capital deployment. Companies controlling the largest infrastructure systems often control the lowest cost structures. When cost leadership combines with scale demand, market power can consolidate quickly. Competition does not disappear, but it moves, not at the infrastructure layer, above it. Because beneath the AI software economy lies a heavier foundation: concrete facilities, energy grids, cooling systems, compute clusters, capital infrastructure. And in the economics of artificial intelligence, that foundation increasingly determines who can compete at scale and who cannot.